In this lecture, we will talk about the Gaussian Poincare inequality. Before I describe this Gaussian Poincare inequality, maybe I can quickly review what is the basic classic Poincare inequality, which is not connected to this course, but perhaps that will help you understand this name. So consider a function f. Sorry about this. Consider a function f from Rn to R. It's a real valued function with n-dimensional domain, such that if you take its gradient, this gradient of this function is an n-dimensional vector, so you can take its L2 norm. Okay, so this is defined as, if you remember this is summation I equal to 1 to n fx whole square. Okay, that's what this. So this is the ith dimension of the gradient, and that this norm is just sum uh, of all the Euclidean length square of the gradient. That's what this quantity is. So suppose that if you integrate this gradient norm, okay, this is a function of x, so I'll just put it just to be explicit, I'll just put it here, and then you take your let's take a Lebesgue measure here. So this is all integrating over entire Rn. Suppose that this is finite. Okay, so f is a differentiable function, continuously differentiable function, and this norm, the integration of two norm is finite. Then Poincare inequality, actually this I'm just writing a very simple consequence of Poincare inequality. Poincare inequality actually extends to any pth norm of this vector, LP norm of this vector. It says that if you look at the pth norm of the function itself, so what is that? So this function, you can take this function, you can look at the value of the function at uh, you can look at the value of the function at x, take its square, and then do the mu. This is the 2 norm of square of the function. This is less than equal to some constant times the pth norm, or the 2 norm in this case, square of this guy. So this is the Poincare inequality. The integration, when we look at this inequality, so maybe I'll write it compactly, a little bit more compactly. So what this says is that look at the function f, look at its L2 norm square, and this guy is less than equal to some c times. Look at this new function, which is the gradient of f. Okay. Look at the this norm. Think of this guy here, and I'll just write it as L2Rn. That's a slightly more compact form of the same inequality. Okay, so this is the Poincare inequality. The Gaussian Poincare inequality that we want to show says that a similar inequality holds when instead of this Lebesgue measure mu, you consider a Gaussian measure on Rn. So that's the Gaussian Poincare inequality. Let me write the statement. So once again, f is a function from Rn to R, and it's continuously differentiable. We also assume that its second derivative is bounded, so let's do that. So if you look at, so I'll just concretely put down what we require to be bounded. Fix maybe I'll just put it this way. So look at the partial derivative, the second derivative along the ith dimension, and take sup over x. So we assume this guy is less than or equal to k. So second derivative is bounded. That's what we assume, which is finite. Okay, so this is the contested differentiable function, and let x be the standard normal random variable on Rn. So this is just the Gaussian random variable with mean 0 and variance 1 along all directions. Okay, so the inequality is then, if you look at the variance of f of x, that must be less than the expected value of norm of gradient of f of x whole square. So pretty clean actually. Okay, this is the Gaussian Poincare inequality. So it looks very much like the Poincare inequality here, and you have you just have replaced all these integrals with integrals over the Gaussian measure. That's what the inequality claims. So why are we covering this inequality? The reason we want to cover this inequality is, first, so why are we presenting this? By the way, this is from the chapter, this is from chapter 3 of the textbook. Okay. The Bouchereau-Lugosi-Massart textbook. This is chapter 3. So why are we presenting this? There are three reasons for me to present this. First is that I think it's very useful. You may find some application where you can use it. Yeah. So that's the first reason to present this. But perhaps more importantly, the proof that we'll show it will show the role of so-called tensorization argument. So that's something that will come again and again in this course, where you will prove something for one dimension and it will extend to n dimensions. Okay, and in this case, the tensorization argument will follow from Efron-Stein inequality, which we saw in the last lecture. Just a second. And the third reason is that this gives an interesting instantiation of Talleyrand's principle that Aditya mentioned in the first class. It said that functions which do not depend too much on any one dimension concentrate well around its mean. And in fact, a good measure of how well the function fluctuate in along any one direction is this gradient. And this is the sum of fluctuations along all dimensions. This is a sum of fluctuation across different dimensions, and this gives an exact bound of variance in terms of fluctuation along different directions. That's what this does. So this can be seen this can be viewed as an instantiation of this Talleyrand's principle, that functions which do not depend on any one dimension too much tend to concentrate around their means. Okay, so let's show the proof. We have enough build up now, so we'll prove this inequality. The proof is very cool. Step 1 is what I'll call a tensorization argument. And I'll just say that it suffices to prove this for n equal to 1. Okay, that's a claim. That if you show this inequality for one dimension, then automatically it holds for all dimensions. So how do we show that? Indeed, by Efron-Stein inequality, the variance of this random variable z, so throughout we'll have z equal to f of x. Okay, that's a notation. We just I think almost throughout this course we'll have this notation, but I'll remind you from time to time. So from variance of this random variable z from Efron-Stein is less than equal to I equal to 1 to n expected variance given all the other coordinates but the ith coordinate. So you have fixed all x1 to xi minus 1 and xi plus 1 to xn. This is something we saw in the last lecture. Now if you look at this variance inside, it has all the coordinates fixed and only one coordinate is changing. So this is exactly a variance of a function for a function which is differentiable, continuously differentiable. This so this is just a one-dimensional function if you have fixed all the coordinates, and therefore if the inequality holds, the Gaussian Poincare inequality holds by Gaussian Poincare for n equal to 1, we can apply it to this inner variance. So what do you get? You get the expected value of right, get the square of that. This is exactly the Gaussian Poincare inequality applied to one dimension, and this expectation actually is over just the ith coordinate. So you fix everything but the ith coordinate. So let me make it capital X. That's where you're evaluating this function, and you fix all but the ith coordinate. So this expectation is this. Okay, so we have just applied. You have to convince yourself that this bound, I've applied a bound here, and this bound is for Gaussian Poincare for n equal to 1. Okay, if this is true, then expectation of this conditional expectation is just the expectation. So this looks like I equal to 1 to n expected value of this derivative of fx evaluated at this point x, and the square of this, and that's exactly, if you can take the summation inside. So this is exactly this. Okay, so it suffices to prove it for n equal to 1. If you have this bound for n equal to 1, which we applied in the second inequality here, then the bound automatically holds for a general n. So now we do the proof for n equal to 1. Proof for one dimension. These are very interesting set of inequalities where you show it for one dimension and they automatically follow for multiple dimensions. And here we used Efron-Stein to establish this reduction that one dimension suffices to prove the general n dimension proof. Okay. Now how do we prove this inequality for one dimension? Okay, so that proof itself is very interesting. So what we have to prove, given let x be standard normal random variable and f, now we can think of it as a function from R to R, be continuously differentiable. Further, we have a bound on the second derivative. Further, f prime prime x. This is some assumption. I should be careful to write sup all the time. Sup over x f prime prime x is it's some k which is finite. Okay, that's the second assumption. And then we have to prove that expected value, variance of f of x, this is just the one-dimensional version, is less than equal to the expected value of f prime first derivative of x square. Okay, that's the one-dimension version of this Gaussian Poincare inequality. How do we show this? Well, again, we'll use, interestingly, we'll use the Efron-Stein one more time. And the idea is we'll approximate this random variable x, using central limit theorem. How do we do this? Oh, by the way, this is something we have to prove. That's what we are proving now. So how do we do that? So let epsilon 1 to epsilon m be independent and identically distributed Rademacher random variables. Rademacher random variables. That is, each epsilon I takes values minus 1 and 1, and probability that epsilon I equals to 1 equals to probability that epsilon I equals to minus 1, and that's how. So we take this Sm as the normalized sum of these guys. So note that the expected value of, I'll note it here, expected value of this Sm is 0, and the variance of this Sm is the sum of variances by m. And what is the sum of variances here? So this is just the variance of the individual guy. What's the variance of this Rademacher random variable? It's just one. Okay, so this is a unit variance random variable with mean 0. So then by central limit theorem, probability that Sm is greater than t for any t goes to the Gaussian tail function. So 1 by root 2 pi integral t to infinity e to the power minus x square by 2 dx as m goes to infinity. This is exactly the statement of central limit theorem. All the tails go to this Gaussian tails. Okay. Right. We will use this. We will use the central limit theorem. But what we will do is we will look at the variance of f of Sm and bound it using Efron-Stein, and we'll get a bound, and then we will use central limit theorem to translate that bound into a bound about variance of f of x. And the claim is that if f is bounded, which in this case it is because the second derivative is bounded and it's continuously differentiable. So if f is bounded, then the variance of fx equals to the variance given by this Sm in the limit as m going to infinity. Okay, that's what we will do. So we consider, let me just write that part, consider variance of f of Sm by Efron-Stein inequality applied once again. So for a very different reason. The previous time we applied it for tensorization. This time we are applying it to break this x into some small parts here by Efron-Stein's or let me just call it the Efron-Stein, by the Efron-Stein inequality. Variance of f of Sm is less than equal to j equal to 1 to m. Now we are thinking of this e epsilon 1 to epsilon m as different independent random variables. So we are applying Efron-Stein in a very different way than what we did before. Variance fixed all epsilon I j's epsilon i's except the jth one, and then look at this variance of f of Sm. I'm viewing this as a function of epsilon 1 to epsilon 1 to epsilon n m. Okay, that's just Efron-Stein. So let's look at this variance a bit more closely. So what is this variance? Remember that this is just variance of, so we have fixed everything and we're just changing one random variable. Um, that's, we can view it as variance of g of just some epsilon j. This is the only one which is changing, everything else is fixed. So this guy equals to, remember this is variance of, this is the expected value, we've seen this before, of half into g of epsilon j minus g of its independent copy epsilon j prime whole square. And when we do it this way, this is the independent copy. Now these two independent random variables, if they are equal, which happens with probability half, so these two signs can equal, so both can be 1 or both can be -1. In this case this will be 0. Only when they are different this will be something. So, and whenever they are different, what you get is the probability that they're different is half, and this is just expected value of this. There's no expectation here, so this is just g of 1 minus g of -1 whole square. Okay, so that's for any function g, and if we substitute it for this one, so this implies that variance, if you fix all but the jth coordinate of this Sm, is 1 by 4 into f of, so Sm, what happens when you fix epsilon j as 1? So first you take Sm minus epsilon j by root m and add to it 1 by root m minus Sm minus epsilon j by root m minus 1 by root m. That's what this function is, whole square. Okay, so we get this expression here for this variance. This is exact equality, and there's an expectation sitting outside. Now, if you look at this guy here, we are evaluating some function at this point and adding and subtracting this 1 minus root m. Therefore, we can bound it by, this is less than equal to, this is equal to 1 by 4 f prime of Sm minus epsilon j by root m, okay, plus 2 by root m and then you have the second derivative coming in. So it's, I'm just putting plus minus, this is all rough, okay, plus minus something here, the second derivative comes in here, but the second derivative, sorry, I'm just doing Taylor series approximation. So this is this minus this is f prime this 2 by root m plus, now the second derivative which is bounded by k plus minus k, and the change again is 1 by m. Okay, k is some constant by 2, let's say 2 by m, 2 by m, 4 by m, so something like that. This may be wrong. This is just a Taylor series approximation. By plus minus I mean it's somewhere in this interval. Okay, So you can square it. In fact, even this guy can be taken here. It's some constant by m again. For the second derivative part, we can take it here again. So this is 1 by 4 f prime sm square plus some plus minus some so plus some constant k prime by m square plus minus some other constant k prime prime. This is just by taking the second part here. Of this. So you have another extra power here. So you have m from this guy and you have root m from here, and you have derivative here, but derivative also is bounded because the second derivative is bounded. So this is what you get roughly. So all these things are bounded here. Okay. So that's what we get here. Now when we take the expectation, see, this is no dependence on j here. I'm all abstracting out all those things by this k prime prime. If this k prime prime is obtained by using this k and again max over f prime, because the second derivative is bounded, this max over f prime is also bounded. That's how I'm writing this. Okay. The important point is that therefore when you sum over this j from 1 to m and look at the variance of j of this f of sm, this is less than equal to this first term is just f prime sm square. Since you have multiplied with m, and all the other terms, I'm just putting some constant here. So this is the dominating term here. So you get this. Therefore, you can take expectation implies that the variance of f of sm, this is what we had here. Here, we change back to the black color so that we can relate to the previous inequality. Let me show you the previous inequality. Yeah, it's here. So variance of f of sm is less than equal to expected value of f prime sm square plus minus some k prime prime by root m. That's what we get. So taking limit m going to infinity of this variance of f of sm is less than equal to limit m going to infinity expected value of f prime sm square plus minus k prime. This thing goes to 0, okay, because this is by root n. Okay, that's the main inequality. Now since f and f prime are continuous functions, and sm converges to this Gaussian in distribution. So this is convergence in distribution. This is my notation for convergence in distribution. You will have that both expected value of f prime sm square. This is also a continuous function. For any continuous function, this is true. In particular, f prime square is continuous. This guy goes to expected value of f prime x square This is just by definition of convergence in distribution. So typically we see convergence in distribution as convergence of the law, the probability law, but from the dual representation of that convergence, you can also get it for as convergence of for all continuous functions, bounded continuous functions. Okay, and variance. So you can get it to expectations, but variance is also an expectation of a continuous function, and therefore variance of f of Sm, because f was continuous, so this is also variance is an expectation of some continuous function. So this goes to variance f of x. Okay, so both these convergence happen as m goes to infinity. Okay, and therefore we have shown that variance of f of x for one dimension case goes to is less than equal to expected value of f prime x squared, which is the Gaussian Poincare inequality for n equal to 1, and already we have shown in the first step that it suffices to prove this thing for n equal to 1. So we are done. So right, this is a very interesting proof where we use Efron-Stein twice. First we used it for tensorization, and in the next step we use it to replace a Gaussian random variable with some of IID Rademacher. Rademacher was just chosen for convenience. You could have chosen any other random variable. Bounded random variable would have been more convenient. And then you got this change. This Efron-Stein gives you relates the variance of f to the change in f when you change one of those random variables, and that we could control by the fact that f was continuously differentiable, and therefore we can use Taylor series approximation. In fact, f was twice continuously differentiable, so we could use Taylor series approximation here. And that gave you a bound for variance of fm in terms of just the f prime sm at that point plus some small change, but there was a division by 1 by root m. So when you take limit m going to infinity, this extra fudge term goes away and you are just left with this clean inequality. And finally we notice that since sm goes to Gaussian in distribution, for any continuous function f and f prime, both these things will go to variance of fx and expected value of f prime x squared. Okay, that's the proof. Alright, so this concludes the lectures for this week. I'll see you in the next week.